Well, hello. I apologize for standing between you and lunch, but I will try to make it quick. My name is Aleksandra Krstic, and I work for the GPU research team at Qualcomm, and it's my pleasure to be here today to talk about ray tracing on our Adreno GPUs. But before I jump into my talk, I would like to acknowledge and thank all of the hardworking ray tracing engineers at Qualcomm. Even though I'm standing here talking about this work, this is collective work of many individuals across many years. And I would also like to thank my leadership for their vision and encouragement and allowing me to be here today. All right, so my talk is kind of split into these 4 sections. I will talk a little bit about Adreno GPUs. Then I will talk about really the 2 parts of ray tracing, the builder part and Traversal. Then I will talk a little bit about the tools that we have to help you develop and debug your ray tracing applications on our Snapdragon processors. But no graphics conference talk would be complete without a demo. So this is a demo written by our Snapdragon studios. It's running on our mobile platform, running UE5 PC console deferred renderer with Nanite, Lumen with hardware ray tracing, and virtual shadow maps. Nanite is chugging through about 540 million primitives here. I don't know how to start the video. Just click. All right. Oh, no. Sorry. Let's see the video. There you go. Thank you. There is also audio, but you can imagine, as they said. All right. Thank you. All right, so as a GPU architect, I have to say that at the heart of our Snapdragon processors are really, for me, our Adreno GPUs. And this is a curated list of our latest GPU features. I won't bore you with the details of everything in here, but we have high-performance memory that is kind of close to the metal GPU memory. We have tall memory heaps, bunch of UE 5 engine, UE 5 advanced optimizations for Adrenos, super resolution, shadow denoisers, as well we support all of the modern languages, Vulkan, DX, OpenCL. But this is a ray tracing talk, so let's talk about ray tracing. So what is ray tracing so that we're all on the same page? So ray tracing is really a query operation. So given a collection of triangles, an array that has a direction, origin, and some extents, what does that ray hit in the scene? What is the first thing that it hits? Meaning what is the closest thing that it hits. So we use it to kind of model light transport. So how does light travel through a scene? It's very computationally intensive. So if you have X number of triangles and Y number of rays, that blows up, the number of computations that you have to do blow up pretty significantly. But don't worry, it's amenable to parallelization and can be accelerated on the GPUs, and many modern GPUs today accelerate ray tracing. On the standard side, both Vulkan and DX offer ray tracing APIs, and our Adreno GPUs support both Vulkan, ray query, ray pipelines, as well as DXR 1.1. So as I mentioned before, ray tracing can be really thought of like it's split into these 2 parts. So we, on the front end, build acceleration structures, and on the back end, we do traversal. So what are acceleration structures, and why do we need them? So any piece of your geometry in the scene can be intersected by any of the rays that you're shooting. As I mentioned before, say if you have 1 million rays and you trace them against 1 million triangles, well, you might need to do 1 trillion ray triangle tests, right? Well, that's quite a lot, and we don't do that. Luckily, APIs have defined these things called acceleration structures that are used to help you kind of represent your scene more efficiently. So we have bottom-level acceleration structures and top-level acceleration structures. So bottom-level acceleration structures, or BLASs, are built over geometry, and top-level, or TLAS, is built over the instances of the BLASs in your scene. These are opaque structures to the developers, so you don't really see how they're represented internally. You just get to provide all the information, your geometry, and some descriptors through your application to us, and then we decide how we want to represent this. Most people use boundary volume hierarchies to represent acceleration structures internally. So what we do this kind of spatial recursive subdivision, and we create these axis-aligned boxes. So they can be any size, they can overlap. We organize them into tree structures, and they kind of bring, and the whole point of this is to bring this complexity down of this traversal operation that we have to do. There are many variants of BVHs, right? There are binary trees, quad trees, they can be compressed, not compressed. So again, it all depends on some secret sauce that IHVs internally use. But the main point here is that the better BVH we build, the faster the traversal will be. So just keep that in mind. So what does that really mean for Adreno GPUs? So how do we represent acceleration structures internally? So our trees are 8 wide. So that means that our internal nodes can hold up to 8 ABBs, and our leaf nodes can hold up to 4 triangles. Both internal nodes and leaf nodes are the same size. They're 64 bytes. So this is kind of very cache aligned for us. So on average, we use about 34 bytes to represent a triangle and about 78 bytes to represent an instance. The way the nodes are laid out in the memory, they're all packed very tightly. There is no empty space. The children are adjacent, but they can be anywhere, laid out anywhere in this memory. And we have random access to these contiguous blocks. So when you're building acceleration structures on our GPUs, some good things to keep in mind are that you want to build on the GPU. We have world-class builders that implement the modern techniques and accelerate building acceleration structures quite well. For kind of full throughput, you want to fill up our machine. So you probably want to send about 500,000 primitives per build. So if you have a lot of small BLASs, maybe you want to think about combining them in one larger one, or you can kind of dispatch them in parallel. Building acceleration structures is a costly operation, so you probably don't want to do it often. You want to refit as much as possible. APIs allow for a couple of different build flags. So there's a fast build flag, and that's about 2.5 times faster than our fast trace flag, but it does not build as good of a tree as the fast trace flag would. Refit takes is about 9 times faster than our fast trace. And you also want to think about potentially amortizing the cost of both refit and rebuild over multiple frames. For our GPUs, we prefer fast trace flag, especially if you have static geometry. You should use that as much as possible because we can apply additional optimization during the build time and get better trees. And you also want to simplify your acceleration structure, right? As somebody previously mentioned, right? If you don't use certain geometry in your scene, please don't send it down. So cull, right? Yeah, it will help the BVH quality as well as build times. On the traversal side, so this is now kind of going to the back end. On the traversal side, right, so what are the traversal steps? So if you can think of, so now we have this tree that we have to kind of, intersect our rays against. So if you kind of think about a bunch of rays going through a wide tree, at each step, we have to do either ray box or ray triangle intersection. So that's a lot of floating point math. And floating point math is okay, I guess. Here, the worst part here is that there's a lot of divergence that happens. So there's like two types of divergence. If you can imagine, again, those rays traveling through this tree, a lot of times every ray wants to probably intersect against a different node, and this node is somewhere in memory. So this is your memory divergence. So this can be very bad for your caches. Or a lot of rays kind of traveling to the tree also have different lifetimes. So some rays hit something very quickly or miss something very quickly, and other rays kind of just want to kind of keep traversing until they find something they hit or eventually miss. So this is this kind of lifetime or traversal divergence, which also can hurt your performance. And because we're traversing through a tree, we require a stack for every for every ray that is in flight, and we keep that stack on our GPU. So what is the hardware that actually accelerates this look on Adreno GPUs? So this is a pictorial description of that. So we have a SIMD64, which means that 64 fibers kind of work together or go through this process together. We actually accelerate stack management as well as ray box and ray triangle intersections. So we have 8 ray box or 4 ray triangle intersections that the rays can go through. So if you remember what our tree looks like, this is mirrored exactly here in hardware. So as I mentioned before, we have 8 white trees with 4 triangles, up to 4 triangles in the leaves. So every ray traverses through goes through the hardware independently. There's no dependencies outside of the SIMD64. And we also have a dedicated node cache where, as I mentioned before, we can store the nodes that the rays want to kind of intersect against. The cache is 16 kilobytes. So at 1 gigahertz, this is just some numbers here, we can do about 12 billion rays per second. That also kind of can be translated to 96 billion ray box intersections per second, or 48 billion ray triangle intersections per second. So this hardware is used to accelerate traversal, and APIs actually define kind of 2 ways to do ray tracing. So there's ray query or inline ray tracing, as well as ray pipeline. So this hardware is used for both. But if you are writing your shaders, your ray tracing shaders using ray query or inline ray tracing, maybe you can keep some of these things in mind. So you can use ray query in any shader stage, but we prefer if you use ray query in compute shaders for various reasons. But one of the big kind of points here is that compute can complete out of order, while your fragment and vertex shaders cannot. There is a certain order that is imposed there. Also, when you are writing your shaders, you want to be mindful of how long they're getting. So if you add proceed to your shaders, we also inline the definition of proceed. So if you kind of sprinkle proceed all over your compute shader or your fragment shader, you will see that that shader will become much, much larger. So you want to be very mindful how many call sites to proceed you actually have. Also keep in mind your GPR usage. As always, apply good programming practices here as well, especially because ray queries are very greedy when it comes to using GPRs. So the more of them you create, the more GPRs you will use, the less you will help something else. So yeah, create a handful of ray query objects, maybe 1, 2, 3, and then reuse as much as possible. Also, don't create custom data structures to copy the data out of ray queries into. Just gonna use the intrinsics that are provided by the APIs to access the ray query data directly. And then there's also ray flags is defined by APIs, and this is very Vulkan-centric, but this applies to DX as well. If you're tracing shadow rays, use terminate on first hit. If your geometry is fully opaque, tell us it's fully opaque. Write nice code so that our compiler can generate even better assembly code for you. Again, use your good programming practices, remove that code. Yeah, just help our compiler help you generate good code. And then you can also use 16-bit precision in your shader if you like. The other way of doing ray tracing is to use ray pipelines. So what is ray pipelines? Well, if I had to describe ray pipelines in kind of one sentence, I would say it's a complex graph which consists of multiple shader types or shader stages and supports recursion. So this picture on the right is supposed to kind of represent visually how complicated ray pipelines can become as kind of defined by the API. So our ray pipeline solution is really robust and kind of keeps the application complexity in mind. What does that mean? So we actually provide two solutions for ray pipelines. We have an Uber shader solution as well as a shader graph solution. So what does it mean, Uber shader? That means that we actually inline all of your shaders as you define them in your ray pipeline into one large shader. And then we dispatch that as a compute shader. We can do this if your ray pipelines are relatively simple. There's not too many hit groups. There's no recursion. The shaders themselves that are present are relatively small. And our other solution is this shader graph approach. So in shader graph approach, we actually just keep all of the shaders that are in that pipeline separate and dispatch them separately. This is for more complicated kind of use cases. And what is interesting about the shader graph solution is that we can actually repack based on the current API repacking point. So for example, traceRay is a repacking point as defined by the API today. All right, and then I am on tools now, so we're going hopefully pretty quickly. So we have a Snapdragon profiler. It's our general profiler that runs on various different platforms and connects directly to your Snapdragon powered devices. It has a bunch of different capabilities. I will just be focusing on ray tracing features that it offers. So it has different views. We have this real-time view that can provide kind of hardware metrics or hardware counters. So some of the metrics for the ray tracing are this RTU busy, BVH fetch latency cycles that will kind of tell you how well the caches are working, how many ray box, ray triangle intersections your workload has, etc. We also have the trace view. So here you can kind of look at kind of the lifetime of your workload and the various events that happen here. So you can look at acceleration structure build operations. You can look at your RayGen or dispatch stages. And all of the hardware metrics are also available in this view as well. We have a snapshot, so this is for capture and debug. So you can capture a frame and then kind of do a deep level analysis. You can look at your resources. You can look at shader, source, shader disassembly, a bunch of different shader stats, right? So this is really good for kind of deep level analysis of your workloads. And then finally, specifically, I guess, for ray tracing, we have this built-in acceleration structure viewer. So this allows you to kind of visualize what we built internally. So you have different colors for different nodes, for AIBV hierarchy. And this can kind of help you identify areas of your scene that you might want to kind of optimize a little bit to build a better tree. In the Snapdragon profiler, you can download it if you just go to qualcomm.com/developer. And yeah, the link is on the bottom of this slide. All right, I think that's all I had. Did I go through that really fast? I guess.